Let us look at the choice of the catalyst. Although TiCl4 worked excellently in some of the reactions what we have seen earlier, they are not always successful. Say for example, in this particular example, if you use TiCl4 at minus 78 degree, we get 0% yield of the condensed product. In this particular case, tin chloride worked better, giving 65% of the product. So, it is always advisable to screen various catalysts under different reaction conditions, that is solvents and different temperatures, to identify the best reagent for a particular reaction. So, it is not always TiCl4 is the best catalyst for this particular condensation reaction. So, we have to screen various catalysts. So, the aldol type condensation of enol silyl ethers and acetals or orthoesters can be accomplished by the use of trimethyl silyl trifluoromethane sulfonate, that is the triflate, TMS triflate. In these reactions, TMSO triflate acts as a true catalyst and is required only in 1 to 5 mole %. As shown here, we require only very catalytic amount of the TMS triflate. The reaction showing interesting chemoselectivity in that acetals are highly reactive receptors of enol silyl ethers, but the parent aldehyde or ketone do not react at all under these conditions. So, the acetals are highly reactive, whereas the unprotected aldehydes are not reactive under reaction conditions. So far what we have seen is that different kinds of carbonyl functions will react differently with enol silyl ethers depending on what is the catalyst we are using. Under the same reaction conditions, chemoselectivity is observed with acceptors having 2 or more different kinds of carbonyl electrophilic sites in the same molecule. Let us take the example here and we find out what is the difference. In general, with TiCl4 as a Lewis acid, aldehydes are more reactive than ketones. So, in this molecule we have an aldehyde unit and a ketone unit. This is reacted with this particular silyl enol ether, and when this reaction is run in the presence of TiCl4, only the aldehyde part underwent reaction and the ketone part PHCO, this carbonyl part, did not undergo any reaction. So, when we have a competition between an aldehyde and a ketone, aldehyde is highly reactive under this particular conditions. Now, if we have a ester and the ketone in the same compound, what happens if we react the same starting material, the silyl enol ethers, in the presence of TiCl4 as the catalyst, we have a ketoester, and in this particular case the ketone part undergoes the aldol condensation reaction, whereas the ester part did not undergo the reaction. So, if we look at between the ketone group here and the ketone group here, they are having different reactivity, although the ketone is the same group. So, this chemoselectivity is possible in the kind of silyl enol ethers in the presence of TiCl4. That is, when we treat phenyl glyoxal and the keto, this is the ketoaldehyde which is a phenyl glyoxal, or the ketoester ethyl levulinate, they both undergo differently with this silyl enol ether to give 2 different products. In the first case, ketone is unaffected, in the second case, ester is unaffected. The trimethyl silyl enol ethers of both saturated and unsaturated aliphatic or alicyclic carbonyl compounds, when subjected to, here we see the regioselectivity of C versus O acylation. So, in this case what happens is, we get the C acylation here as 60%, but O acylation is also possible, but that reaction occurs only with 6% yield only. So, here the driving force is the presence of this BF3, that is the Lewis acid. So, this is very crucial for this C alkylation reaction. Next, we have the cyclopropanation reactions of silyl enol ethers. Trimethyl silyl enol ethers of both the saturated and the unsaturated aliphatic or alicyclic carbonyl compounds, when treated with cyclopropanation, that is Smith's reagent, Simon-Smith reagent, that is zinc silver coupled, is used, and the hydrolysis of the product is replaced by the pyridine workup, led to the siloxycyclopropane derivative, which are very useful synthetic intermediates. So, here we can do the cyclopropanation on the ene part, that is the alkene part can undergo cyclopropanation. So, this is a different type of reaction. So far the reaction what we have seen is the silyl enol ether underwent reaction where the double bond is converted, the addition took place here, but here we are doing the cyclopropanation on the alkene. Let us compare the reactivity of silyl enol ethers, enamines and enolates. Although enol silyl ethers are ambient species capable of reacting, so in the case of silyl enol ethers, the superior stability, that is they are non-charged enol equivalent, enolate equivalent, but they have low nucleophilicity. So, for the reaction to occur, we need a Lewis acid which can activate the carbonyl compound. So, that is required for the reactions of silyl enol ethers. In the case of enamines, they are having superior stability similar to silyl enol ethers, and they are also moderately nucleophilic. So, those reactions can be catalyzed in the presence of acid, or in some cases without the acid also this reaction can be catalyzed. These are also non-charged enolate equivalent, and when we talk about enolate, they are poorly stable. So, that is why they are highly reactive and they have high nucleophilicity. So, the reactions are generally carried out low temperature. These are the charged enolate equivalents. Because of the high nucleophilicity, they also react with the weak electrophile like Ri, esters, all those reagents can react with the enolates. In the case of silyl enol ethers, they require strong electrophiles for their reaction, and in the case of enamines, they can react with moderate electrophiles like acid chlorides, aldehydes, etc. Here we are comparing the reactivity of silyl enol ethers, enamines and enolates. If you look at the increasing the nucleophilicity, the reaction rate also increases tremendously for the case of enolate ions, which are extremely high, whereas enol ethers are practically non-reactive, whereas enamines are in between these two extremes. So, from the same carbonyl compound, let us take this is the carbon, this is the carbonyl carbon, we can actually use by changing the different reaction condition, that means by making an enolate anion or making a enamine or by making the silyl enol ethers, we can actually convert the carbonyl compound into various reactive functionalities. So, with this we conclude the comparison, and enolate, enamines and enol ethers, the reactive intermediate species are completed.